All right, so 2.9 is called logarithm expressions. Again, a review of Algebra 2 skills, but we go a little bit further. Actually, we go a little bit further after this section. Almost everything from this section will be something that you've seen before. That's the good news, okay? We start with just the definition of a log function with a base. So first of all, in the expression log base a of x, which is how this is read. So the base is the number on the bottom. We would read that as log base a of x. In that scenario, x would have to be greater than 0. It cannot equal 0, and it has to be greater than 0. So whatever's next to this log cannot be negative. You can't find the log of a negative number. And then your base, the little guy next to your log, this guy will also always be greater than 0. And it won't be 1. Okay, it could be a fraction, but it won't be 1 because 1 to any power would just result in 1. So there would be no change there. It would be a constant, not a log. And the way we go from one way to the other, that is actually it's actually a question on your AP class homework. Literally take this log expression, put it into exponential. So it could be as foundational as that, okay? How we switch from log to exponential is the base on the log comes over and picks up the number that's on the other side, or the variable in this case that's on the other side. So a to the y, and it drops off, leaving the x by itself. If you had Miss Corey, she teaches you bay, right? Like the base, and then the a, and then the e. Yeah, throwback. Shout out to Miss Corey. Sadly, I will teach it as though it's a relationship, and no relationship stays together. Okay, it's like a high school relationship, let's say. Not yours. I'm sure yours will last forever and ever and ever. Okay, but in the log relationships, they never stay together. One always ditches the other. So whether it's on the right-hand side where we're going from log to log and then to exponential, or exponential to log, the pairings never stay together. So this a literally ditches the x, comes over and picks up the y and leaves the x by itself. And in the reverse, this pairing will never stay together. So that base on the exponential function, the a, becomes the base on the log. The x joins it, and the y is left by itself. So no pairing is left together, whether you're going from log to exponential or exponential to log. Okay. So the function makes it an f of x. This is now a logarithmic function. We will start to do some real world stuff with log functions after this section, okay? We will get into a log regression using your calculator after this section, so that will come after your test. The test itself will just have kind of like the foundations of log. So if you want to go from log form to exponential or vice versa, okay, if I'm going from log, like the example that's here, log base 2 of 8 equals 3, it has to be a true statement if they're all numbers, because 2 to the third equals 8. So the 2 comes over, picks up the 3, and drops off, leaving the 8 by itself. You need to know how to go in both directions, from log to exponential, and then also from exponential to log. So the base on the exponential function becomes the base on the log. Those two part ways, the 8 comes over with the log, and the 3 goes to the other side. Again, some of your questions might simply ask for you to convert from exponential to log, or log to exponential. They will refer to what's called the common log, okay, which means just log. When you see just log by itself, it means log base 10. So on your calculators, you have a log button. That log button is log base 10. And you will see it written as log, and you will have to know that that is the same thing as log base 10, because there's going to be times in which you're going to evaluate that, and you'd have to know that that's the base, okay? So if you saw a log of 10, for example, I would know that this is really log base 10 of 10. And when the base and the number next to it are the same, that would simplify to be 1, because if I didn't know it and I wanted to set it up into an equation form, 10 to the x would equal 10, and 10 is raised to the first power, right? So x would be 1. The goal would be to get so good at these logs that you can use mental math to get to them. So if it said log of 100, what you're really saying is, what power do I raise 10 to get to 100? What's that answer? 2. So I think people who like mental math, like people who hate showing work, tend to like logs because it's a lot of mental math and not a lot of work, okay? All right. So example 1 says literally just rewrite the log equation as an exponential equation or vice versa. So we're just rewriting these. So on A, the 4 comes over and picks up the -1. So 4 to the -1 would equal 1/4, would be that in exponential form. And if I want to write the exponential into log, I get log, the base of the exponential becomes the base on the log, the 1/2 goes to the other side, and the 5 joins the log. So we switch spots. We remember this? Yes? Okay, good. All right, now we get, again, quick mental math. So let's see if you can do these. Log base 3 of 3 would be what? 1, because 3 to the first power is 3. B, 3 to what power gives you 81? 4. C, log base 3, -9. 3 to what power gives you a -9? What does a negative do on an exponent? Moves it to the bottom. Can a base that is positive ever turn to negative? No. This is a trick question. No solution. Okay? You can never make a base that is positive result in a negative number. You can never find the log of a negative number or 0. So if 0 or a negative number is there, it's no solution. All right, log base 36 of 1/6. So how do I get from 36 to 1/6? So the negative is going to move it to the bottom, right? So if I'm looking like this, 36 to what power equals 1/6? The negative moves it to the bottom, so I do need it to move to the bottom, right? But I'm going from 36 to 6. What's that exponent? 1/2. It is a square root, and a square root is a 1/2. If it was the other way around, if it said log base 6 and it was 1 over 36, now it'd be -2. The negative would move it to the bottom, and 6 squared would be 36. So if the base is bigger than what you're trying to find, it's probably a root. You just got to figure out if it's a, if it's a square root, it's 1/2. If it's a cube root, it's 1/3, and you would keep going. Yeah.
When it says evaluate, do you put x equals 1?
No, you brought in the x, so you don't need the x as your answer. You literally are just simplifying it. All right, E, log 1,000 would be 3, because 10 to the third equals 1,000. The 10s are easy if you just count your zeros. And log base 3 of 1, 0. What power do I raise anything to make it 1? And it's 0. Good so far? All right. Now, the first part of this is going to be evaluating without the calculator, and then we're going to evaluate with a calculator. So the way I write it without a calculator, this is called change of base, is you put log of the bigger number by way of physical size, not value. So the biggest thing there goes in the top. I would rewrite this as log of 17 over log of 3. That is called change of base, and that is a ratio of common logs. The bigger by way of like literally the location, not the value. Yep. Think base bottom. So the base on the log always goes in the bottom. So if it said log of 17, 3, now it's log 3 over log 17. So whichever one is physically larger, not by value, but physically larger goes in the top, okay? Now grab your graphing utility, okay? There is 2 ways to do this. One is type it in like the way we rewrote it, as a ratio of common logs. So I can do log of 17, I'd have to close the parentheses, divided by log of 3. And this is 2.5789. You also have a button on your TIs that will allow you to change the base on the log. If you go to math and you scroll down to log base. So if I go to the math button, if I go to math and I scroll down, A says log base. If you click that, it gives you the little log with the base. So I put the 3 in there. Oops, not 6. I put 3 in there. And then I put the 17 next to it. And it gives me the same answer. So that's in your math menu. I don't know if that's something that Desmo's calculator has, to be honest. If it does, feel free to use it. But if not, you should be comfortable using your own.
Sorry, but you said the bigger log is dividing will always go on top.
Correct. So base, bottom. Think the little guy that's next to the log is the base is the bottom. Yep.
How come, so even though it says without a calculator, we can use a calculator for the.
No, it says without a calculator and then with. Without a calculator, it would be left as your ratio. With the calculator, it would give you that guy.
Oh, all right.
Yep. Questions so far? Okay, you are going to see some real world examples, and you'll see something in your in the AP classroom using log scales. So a log scale is used to display numerical data over a wide range of values to make it easier to visualize / work with. Meaning, if I have something that eventually gets so large that I want to show it on a scale, I will adjust the way that it is represented. So if I use a log, it's like using, for example, if it's base 10. 10 to the first obviously is 10. 10 to the second is 100. 10 to the third is 1,000. It grows exponentially. So what you will see is things like a Richter scale, which is used to measure an earthquake, is actually using logs, okay? Because when you hear something, let's say it says it's a 2.0 on a Richter scale, that does not mean like it went from 1 to 2. A Richter scale uses logs. So it meant that it was 10 times more intense than the first one because it went from 10 to the first to 10 to the second, if that makes sense, okay? So you will see logs, like there's a question, it's a weird question, I'll be honest, on your AP classroom in which it asks you about Richters. I'm not going to give you the answer because I want you to try to figure it out, okay? But you will see logs used in that way. I added this one on because this is a question that will pop up. So if you downloaded yesterday and it's not there, just take a screenshot of this. But if you downloaded today, it's here. This is the other way that you'll see them, okay, is just like we did before, a real world scenario in which it gives you a function and then you plug in. The sales of a new car in cars per month is modeled by the expression 350 log 25 times t plus 60, where t represents the time since the sales of the car began. How many cars are sold per month for time t equals 40? This would be on the non-calculator portion of your test or or AP exam. So all I have to do is plug in the 40. I get 350 times log of 25 times 40 plus 60. And then 25 times 40 is 1,000. So if I didn't have a calculator, this would have to be something that would be able to be solved using a whole number.
This is on a non-calculator.
This would be on a non-calculator. Yep. So what is log of 1,000? 3, right? Because the base on that log is 3. 10 to the third is 1,000. So this becomes 350 times 3 plus 60. 1,050 plus 60, or 1,110. It could also give you a log with a different base. Like let's say that log was changed. Let's say it was 350 log base 5 of something plus 60. That would mean whatever's going to happen inside that parentheses would be something that's a power of 5. You might get 25 in that parentheses, or 125 in that parentheses, or 625. But something that can be simplified without a calculator, okay? And then we will eventually bring in the LNs, which are your natural logs, but that will happen after your test because this is where we're going to cut the content. Questions?